So we continue with our design of a high performance amplifier that we had started last time. Just to quickly recap, we had set for ourselves these specifications. So an overall voltage gain of 25,000, input resistance 2 mega ohm, output resistance less than 5 ohms. The collector current to stay between 1 milliamp and 10 milliamp, and to use only DC coupling across stages. And last time, this is the block diagram we had come by the end of that lecture. We had said that the first stage has to be a common emitter amplifier with emitter degeneration. And in fact, we had just finished the design of this first stage. So what we had designed was this first stage with Q1, an emitter resistor, a collector resistor, and the output taken at the collector. And we determined values last time, and what we had found was that the voltage gain of this stage was coming out to be minus 0.33, and we said we live with it. And then this is the second stage, which is a gain stage. Okay. So now let's start the second stage design. From the first stage, we know that this collector voltage is 0.7. So the base voltage of Q2 will be 0.7. So the emitter voltage would be 0 volts. So that's what is here. And we had already discussed last time that we'll make the collector current, in fact, of all gain stages to be 1 milliampere, the lowest possible, so that the R-pi of that stage is the highest possible, which was 5 kilo ohms. So we say the current here is 1 milliamp. This voltage is 0, this voltage is 12. So the RE2 has 12 volts across it, 1 milliamp through it. And so RE comes out to be 12 kilo ohms. So we choose RE to be 12 kilo ohms. The next question we ask is, how about RC? What value of RC2 to choose? RC2, of course, decides the voltage gain, and it also decides the DC voltage at the collector of Q2. So first let's start with the voltage gain. What is the expression of the voltage gain? Now we are wise. We burnt our finger once. Now we know that the second stage gain will depend on the third stage, because the second stage is loaded by the third stage, and the Rin of the third stage will come in parallel with the RC of the second stage. So, and the Rin of the third stage will be R-pi, because we have planned for the third stage also to be a gain stage. So the emitter resistor is bypassed, so Rin is only R-pi. And okay, so we'll draw the circuit. So this is a third stage we've drawn here conceptually. And that, so the R-pi of Q3 will load the second stage, or basically R-pi 3 will come in parallel with RC2. So here is the equivalent circuit. This is the, what is this here? Yeah, this is the second stage. This is the third stage. And basically we want to find the gain of the second stage, VC2 by VC1. And in the second stage, the R-pi 3 comes in parallel with RC2. So this expression is minus Gm times that resistance. So the gain of the second stage is minus Gm2 times RC2 parallel R-pi 3. Now, of course, we would like this gain to be as high as possible, because this is a gain stage. So from this expression now that we have this, we conclude that for the gain to be as high as possible, RC2 must be as high as possible, and R-pi 3 also must be as high as possible. Alright. Now let's think of the effect of RC2 on the DC voltages. So the larger the RC2, the smaller will be VC2, and the smaller will be the voltage swing at the output of the second stage. So let's look at the circuit again. So here, if RC2 is larger, it has and the current is 1 milliampere. So the larger the RC2, the lower is this DC voltage VC2. VE2 is fixed to be 0 volts. So the lower VC2 becomes, the smaller will be the voltage swing at this node for AC signals. So the next question we ask is, well, how much is the voltage swing we required here? Because based on that we'll choose VC2 to be as low as possible, so that the gain is as high as possible. Okay, so the question you ask is, what is the swing we need at VC2? Okay, so for this, let's look at the complete block diagram. So this is our block diagram. We already know this gain is 0.33. This gain is 1. It's an emitter follower. The overall voltage gain is 25,000, which will be the product of the 4 gains. What that means is that the second stage gain times the third stage gain must be 75,000, which is 25,000 divided by 0.33, or in other words 0.33 times 75,000 will be the overall gain, which must be 25,000. For now we don't know these gains individually. Just to get a ballpark figure, let's assume that these gains are about equal, so that the square of, well, this gain times this gain 75,000, so each of the gains will be a square root of 75,000, which comes out to be about 280. Alright, so this is what we have. We have a gain of 280 here, a 280 here, 0.33 here. Now let's assume, in fact this is not given in the specification, it could have been, so I'm going to say that this is in effect a specification, that the swing at the output is 5 volts. We'll design for a voltage swing at the output of 5 volts, and by swing I mean an amplitude. So we are all dealing with sinusoidal signals. So the sinusoidal signal at the output will have an amplitude of 5 volts or a peak to peak of 10 volts. Alright, so we'll assume that. So the swing here, or the AC amplitude at the output, is 5 volts. So the AC amplitude here will be the same because the voltage gain is 1. The AC amplitude here will be this amplitude divided by 280. That is the amplitude possible at VC2. Alright, so that is 18 millivolts. 5 volts divided by 280. The AC amplitude here will be this amplitude divided by 280, which is 64 millivolts. So the AC amplitude here will be 64 microvolts. Okay, what is the meaning of all this? The meaning of all this is that when the input amplitude is 64 microvolts, the output amplitude will be 5 volts, and that is basically the amplitude that we have designed, we will be designing for, so that if the input amplitude grows greater than 64 microvolts, then the output will experience some clipping or some distortion of the output signal. So the input amplitude will not be basically allowed to go above 64 microvolts, because then we'll get distortion at the output. Which means that the amplitude we expect here at the output of the second stage, the first gain stage, is 18 millivolts. The swing at the output of the first gain stage is 18 millivolts, which is of course very small, which means that our DC collector voltage at this node can be very close to the emitter voltage. So we say the DC collector voltage can be very close to V2 plus 0.2, the 0.2 required to keep the transistor in the active mode. And we are doing this because the smaller the VC2, the larger is the voltage gain of that stage. VE2 is already 0, we already know. So VC2 can be 0.2. Let us set it to be 0.5. Here, there, doesn't matter. So let's say 0.5. So RC2 then will be 12 minus 0.5 divided by 1 milliamp, which comes out to be 11.5 kilo ohms. Now we don't have 11.5 kilo ohm available. We have a 10 and we have a 12. Now if we make this 12, if we make RC2 12, then VC2 will become 0, right? Let's look at the circuit. If this is 12 kilo ohms and 1 milliamp flows through it, then the voltage across RC2 is 12 volts and this node voltage will be 0. This node voltage is already 0, then the VCE of Q2 will become 0 and the transistor will go out of the active mode. This is not not permissible. We don't want that to happen because then we'll not get any gain out of Q2. So we cannot make RC2 12 kilo ohms. Let us make it 10 kilo ohms. Alright. If this is 10 kilo ohms with a 1 milliamp, VC2 will be 2 volts. Of course, we can make RC2 11.5 by connecting two resistors in series, a 10K and a 1.5K. It's easy to do. Putting resistors in series is not a big deal. But if I leave it to you to calculate how much difference this makes to the gain of the second stage. Okay, just calculate the gain for an RC2 of 11.5K and an RC2 of 10K. Homework. For now, we'll keep it as 10K. So then, so then let's find the gain of the second stage with this value of RC2. So we already saw that the expression of the gain is this. We are saying R pi 3 will be 5 kilo ohms. So we have all the numbers. So the gain turns out to be minus 133. It's not as large as we had planned. We had planned for 280. It is smaller. In fact, generally you recall our discussion of single stage common emitter amplifier. The gain was in the range of 240 to 300 or so. So this should have happened. The reason it did not happen here is because loading R pi 3. Because of R pi 3, the gain has gone down. So if, for example, if you remove R pi 3, then you have IC3 over VTGM is 1 by 25, that's 40, and this is 10K, so we would have got a gain of 400. Without R pi 3, we would have got a nice gain of 400, but loading. Therefore, the gain has come down to 133. Alright, let's continue. We'll see what happens. Come back later. Alright. So now we finished stage 2. Let us do stage 3. So this is a circuit of the stage 3. The circuit is identical to stage 2. It is a gain stage common emitter amplifier with the emitter resistor bypassed. We already know that VC2 is 2 volts. We just designed for it. So VE3 will be 1.3 volts. Again, we are designing for 1 milliamp, the lowest possible current. In fact, we already decided that because we already decided that R pi 3 is 5 kilo ohms based on a 1 milliamp current here. So in order to get 1 milliamp to flow, we need an RE3 value of 1.3 plus 12 by 1 milliamp. This voltage is 1.3 minus plus 12 divided by 1 milliamp. So we will get RE3 equal to 13.3 kilo ohms. So now here the available resistors are 12 and 15. That may be too much of a variation. So here we will make RE3 as a series of two resistances, 10 kilo ohm and 3.3 kilo ohm, which will give us 13.3 kilo ohms. So we've decided RE3. Now we must choose RE3. I'm sorry, RC3. RC3 again will be determined by what is the voltage swing we need here. Now let's go back to the full circuit. Going back and forth here. Okay. So this is our full circuit. Recall that at the output of this stage we are going to connect an emitter follower which will have a voltage gain of 1. We want an output swing of 5 volts at the output of the emitter follower, and because the gain of that invisible emitter follower stage here is 1, we need a voltage swing here also of 5 volts. Alright, in fact actually we did see this. Where is it now? I've lost it. Here. So we said that the voltage swing here has to be 5 volts, which is here. So the voltage swing needed here is 5 volts plus minus. So about the DC, this voltage should be able to go up 5 volts and go down 5 volts. How much is V3? E3 is 1.3. So at least plus 0.5 we need. So 6.3. Alright, so we need at the VC3, the DC value has to be at least 6.3. We'll make it 7 just for the nice round number. So we make VC3, we design VC3, the DC voltage to be 7. So that we get a voltage swing of plus minus 5 volts. Alright, 5 volts, 7 volts here, 12 volts here, 1 milliamp flowing through this. So 5 volts by 1 milliamp, RC3 has to be 5 kilo ohms. Alright, so we've finished designing the third stage also. 5 kilo ohms here, 13.3 kilo ohms at the emitter. Alright, now let's find the third stage gain. The expression is the same. VC3 by VC2, the third stage gain is equal to minus GM3 RC3 parallel R in 4. So let's go back. GM3 of this transistor times RC3 in parallel with the resistance, the input resistance of the next stage, R in 4. Okay. Now the next stage is an emitter follower, and the emitter follower is going to have a very large input resistance, many hundreds of kilo ohms. So for now let us assume that this is much larger than RC3. So the parallel combination will simply give RC3. So the gain of the third stage is basically minus GM3 RC3. GM3 is the same, RC3 5 kilo ohms, we just found out. So this gain is minus 200. Okay, now let's think back a little. So this is minus 200. Here we just discussed that we said this was minus 133 because of the loading of RPi3. But if RPi3 is not there, then the gain was coming to be 400. Here we are getting 400, but there we are getting 200. Where did the factor of 2 go? The factor of 2 went in the fact that we need a larger voltage swing here. So because we need a large voltage swing here, VC3, the DC value has to be higher, and so the RC3 has to be lower. RC3 is 5 kilo ohms, RC2 was 10 kilo ohms. Half the value of the resistance, half the gain. So this is minus 200. Okay, now let's put it all together. So we have 3 stages. We've designed for all the resistance values. We've designed for all the currents, all the DC voltages. We found all the gains. So we put all the gains together. Minus 133 minus 200, multiply all the gains. The gain is coming out to be 8778. Red. But we need 25,000.